Now we will start with the presentation of the reference network model. I am Carlos Mateo and I will introduce a general overview of the models, and then José Pablo Chávez will continue with some case studies and examples. So first, regarding the pool, the application of the models, as we will see, involves regulation of distribution system operators. That was the initial application of these models. They can also be applied for analyzing the impact of distributed energy resources, such as storage, photovoltaics, wind, demand response, all kinds of distributed energy resources. They can also be used to build representative networks, as we will see. Initially, these models are not intended for transmission. They are most focused on distribution. Despite we could try to apply similar concepts for transmission, but in general, transmission has different characteristics. In that case, it is more feasible to analyze individual installations. However, in distribution, there are millions of installations, and therefore these models are more useful. And regarding the operation of distribution network, it is not the focus of the model. They are more intended for planning distribution networks, although they have some simplified modeling, but not for hourly profiles for the entire year. So now we can start with the presentation. First, we will start with an introduction about the need of reference network model, explaining how to build reference networks, and presenting some case studies. Finally, we will continue with further work and queries and answers. So first, with this introduction, the integration of new smart technologies in power systems requires technologies analysis, which can be engineering-based, and economic analysis, which can be engineering-based or driven by economists. And this type of analysis may involve the short-term operations, so power flows of electricity, and also the infrastructure of telecommunications required for algorithms such as voltage control, and also a mid or long-term analysis related to the planning of the network, deciding optimal reinforcement and new infrastructure. The focus of reference network model is on the mid and long term, so not on the short term, not on the operation of the system. And questions which typically arise when making this technical analysis are how scalable are the results and how replicable they are. So for example, if you make an analysis on a network, what happens in other networks, and what happens not in a single network but in full Europe or anywhere in the world. So these are questions, and in this case, simulation models can help to answer these questions, because it is not needed to develop the technologies, but you can make simulations on a computer. And finally, about the need of typical representative distribution networks, they usually include medium and low voltage. In some cases, this network also includes high voltage, but not in every country. And they must be based on regional standards and regulation. A reference or representative network is a theoretical, so a synthetic network that can be used as an objective reference for actual grids. And there are two main alternatives. So we have reference network models or non-models. In this case, these models are large-scale optimization models which rely on geographical information. These models require the single location and demand of every consumer, and they provide the regulator with an estimation of the efficient cost that should be incurred by a distribution company supplying a certain geographical area. And they have been applied, for example, in Spain, Sweden, and Chile. And representative network of feeders are a type of reference network model that may rely or not on geographical information. In this case, the coordinates are not so critical. It can be only an electrical model without coordinates. And they can be considered appropriate to describe the behavior of a set of clusters or real distribution networks. They are mainly proposed to benchmark continuity of supply or to regulate distribution costs in Brazil. and also to study future network concepts, for example, in United Kingdom, Italy, and in EU-funded projects. And we have also a concept that could be included in representative networks that are standard or test networks. And we have examples of this in IEEE test networks and SIGRE. We will continue now. This is reference network model are a tool to reduce information asymmetry. This was the initial application of reference network model. This was the revenue cap formula in Spain in 2008. So in this formula, we had a regulatory period in which the remuneration was updated. So here, the term R represents the base remuneration, which was updated every year. And in this case, you have to update it from the year N-1 to the year N. You have to first discount the incentive in quality of service and losses, which are terms Q and P. Then you update it with the price index with term IA, and then you increase it with the allowed change in revenues to taking into account new demand or additional connections. So the term Y would be the new network investment required in order to allow an increase of demand or new distributed generation, for example. And then the terms Q and P are the incentives for quality of service and the incentive for energy losses. So this is the base remuneration. This is the adjustment to take into account price indexes. This is the allowed change in revenue to take into account new demand or additional connections. And this is the incentive for quality of service, and this is the one for energy losses. So how could we apply the models? In principle, the models could be applied. This was not the initial application, but they could be applied for the base revenue at the beginning of the regulatory period. They could be used to contrast the information from the distribution companies. They could also be used to contrast the information of the change in revenue to take into account new demand or additional connections. And they could be used to make analysis on quality of service and losses. And these applications of the reference network models, in principle, the application that was used was for the allowed change in revenue, for this one, and they require a lot of information for the regulator. So in this case, the reference network model can be used to reduce the asymmetry of information with the distribution companies. There are two models, the greenfield model and the brownfield model. The greenfield model plans the whole distribution network to connect consumers and distributed generation to a transmission substation without considering the existing network, but taking into account the same technical constraints and the same planning criteria and the DSOs. And this model can be useful to support in the calculation of the base revenue on the term R. And the brownfield model is used to expand a network to connect additional vertical and horizontal demand given the initial network and considering the same constraints. And it can be useful to support in the calculation of the allowed change in revenue to take into account new demand or additional connections. The main features of the models are, first, they are large scale. They are able to deal with millions of customers. So we can model in a single network with 2 million customers, for example, so really large scale, because most of the planning models are always focused on small networks. They plan the network installation required with the technical parameters and the cost. So we have both concepts, technical parameters and cost parameters. They design low, medium, and high voltage networks. They take into account the differences between urban and rural areas. So they identify settlements, and in this way they can identify what is urban and what is rural and apply different criteria in rural and in urban areas. In principle, the objective of the model is to find the most cost-efficient solution that is able to supply demand and connect distributed generation. And they take into account technical constraints, current and voltage limits, geographical constraints, and reliability targets. And the main inputs of the models are the power, the demand, and the GPS location of every single consumer. So we need for every single consumer the coordinates and the demand, as well as this information, so install capacity and GPS location of distributed generation. It is also required a catalog of equipment and parameters, and the main outputs are the cost efficiently incurred required to build the network. This is for application related to regulation of distribution system operators, and also the topology of the output network, including also the technical parameters and the cost of the equipment. This is the typical structure of the distribution grids. So in this slide, you can see that we have several voltage levels. So we start with the high voltage network, then the medium voltage network, and then the low voltage network. We also have the substation, the transmission substation, which is the origin of these networks, the high to medium voltage substation, which connects the high voltage network to the medium voltage network, and the distribution transformers, which connect the medium voltage network to the low voltage network. The inputs to the models are the low voltage customers, the medium voltage customers, the high voltage customers. Transmission substation is also an input to a model, and also the distributed energy resources in low voltage, medium voltage, and high voltage. And here this number indicates that the upper voltage level have few installations, for example, 10 transmission substations. However, as you go down in the voltage level, the lower levels have millions of installations. Therefore, it is very difficult to analyze installation by installation, and that is why these models are so useful. And the results of the models are CAPEX and OPEX of lines, transformers, substation, every type of equipment which is modeled. The inputs to the models are, first, the geographic consumers and the transmission substation, involving coordinates and demand of the consumers. Also, a catalog of standard equipment, including, for example, substation, electrical lines, capacitor banks, maintenance crews, equipment to improve reliability, all of these equipment with the technical and the economic parameters. Also, there are some general parameters which can be technical and economic, such as the discount rate, which is used to calculate net present values, the demand growth, because these models take into account that the distribution network is sized to be able to deal with an increased demand growth. Simultaneity factors, because not all the demand of the consumers is simultaneous. Loss factor to calculate losses. And also geographical data such as topography, nature reserves, and lakes. When the location of the model is when the location of the consumer is unknown, because the requirements of this model are huge, there is a module to identify the coordinates of the consumers. So in this case, you start with a street map image with a city, for example. Then you identify the contour of the buildings and the streets, and then you locate customers around the block of buildings. And therefore, you have the location of the consumers to be able to apply the models. So once you have the location of the consumers and the demand of the consumers, then you can start planning the network. Planning is applied first to low voltage, then in medium voltage, and finally in high voltage. And in high voltage, the location of the transmission substation is an input to the model, as I commented. So the process, for example, in low voltage is this one. You start with the location of the low voltage consumers, here in this figure. Then you continue planning the distribution transformers, which are these red circles. And then you plan the low voltage feeders, which are these lines. In this way, you plan the low voltage network. Then you apply the same process to plan the medium voltage network. In this case, you plan the substation and then the medium voltage networks, and the same process for high voltage, but in this case the transmission substation is already known. The planning models take into account the geographical constraints interacting with a module which is called the Geographic Information System, the GIS. So the planning model have to decide what is the topology of the high voltage network, medium voltage network, and low voltage network, and which is the location of the high to medium voltage substation and the distribution transformers. And when they are planning the substation and network, they interact with the Geographic Information System. So in this case, they obtain the location cost, and for the network, the path of the electrical lines. This is provided by the Geographical Information System, taking into account topography, natural reserves, and in general, forbidden waste route. There is a module to automatically identify the settlements. So in this case, this is the contour of the settlements in red, and these are customers inside the settlement, and these settlements are automatically identified by the model. So in this case, it detects that the distance among this part of the customers is large, and so it decides that this is a settlement and this is a separate settlement. And it identifies this contour of the settlement, this red line. This is not an input, but automatically decided by the model. And in this way, it can detect what is inside the settlement and is urban, and what is outside the settlement and is interurban. In urban areas, the models are able to plan correctly the networks, and in urban areas, the feeders are constrained by a street map which is automatically calculated by the model, so that the feeders do not cross buildings. This is not a network. This is a street map automatically calculated by the model with the contour of the block of buildings, and this is a graph where the nodes are the customers and the lines are the possible paths for the lines. So, for example, these are not all electrical lines, but these are the possible paths for the lines. So in this case, this street can only be crossed here, here, and here, but not in this part. So this is the street map that the network must comply with. And this is an example of what is the impact of the street map. So on the left, you have a network built with a street map, and on the right, a network built without a street map. So that you can see that the network on the left is more realistic than the network on the right. Here, the medium voltage network is represented in red. The distribution transformer are these cycles, and the low voltage network is represented in black. And you can see that without a street map, the lines cross through the buildings. So this is not realistic. And you don't have this problem when you consider a street map. And it is not only that visually it is more reasonable topology from a topologic point of view, but this also has an impact in the network length. So for example, this network with a street map has a length of 1,400 kilometers. And without a street map, the length is only 1,200. So more or less, there is an impact of about 10-20% of the network length considering a street map or not considering the street map. In rural areas, the models are able to plan the network considering several farms and settlements. For example, this is a network with 4 settlements. This is a settlement, this is another settlement, and this is also another settlement. And although the networks are large scale and you can see the connections among the settlements, the model also plans every detail inside the settlement. So for example, here you have a zoom in of this settlement, and you have all the distribution network inside that settlement. And outside settlements, the network are constrained by forbidden waste rules such as lakes and nature reserves, and they depend on topography. And in case of considering these constraints, the lines wouldn't be straight. So this is an example, for example, considering the geographical constraint, topography and nature reserve. So you have these level curves modeling the topography. Also you have a nature reserve here. And you can see that the electrical lines, which are these black lines, do not cross through a nature reserve. So they avoid this forbidden waste rule. And this also has an impact in terms of network length, as it happened with the street map. This is an example of a network in the US built with reference network models, but in this case the location of the customers was random. So the network doesn't look as realistic as in this previous example, in which we were modeling in detail the coordinates of the consumers taking into account a street map, and these networks are more realistic for the city. This is also an example of a urban network and a semi-urban network. In the urban network here, you have every feeder is represented with a different color. So, for example, this green would be a feeder, this cyan would be another feeder, and you have loops among the feeders, which are these black lines here connecting several feeders, here and here also. And you also have the diffusion transformers, which are small cycles represented here, and the substation here. And this would be a semi-urban network in the outskirts of a city, and in this case it has two long feeders, one here and the other here. And you can see that there are also loops connecting near the end of the feeders to improve reliability. And this is an example of network in the US. So in the US, the networks have different characteristics. So in Europe, it is typical that you only have three-phase networks. However, in the US, you also have single-phase feeders with phase A, B, and C. So this network is an original network from empty test feeder J, where in black it is represented the three-phase feeder, and in the colors blue, green, red are represented single-phase feeders with each of the phases A, B, and C. And this is the original network. So we try to replicate this network using the coordinates of the consumer and applying the reference network model. And this is the network that we obtain with the model that is very similar to the original network. So in this case, this is the three-phase feeder, here and here. And you have the single-phase feeders connecting the consumers. So the networks are very similar, with one single feeder for connecting all the consumers, and with similar distribution of the proportion between single-phase feeders and three-phase feeders. So these are results that we have been obtaining in a project with the Department of Energy in the US from ARPA-E. And well, okay.
Thank you, Jose Pablo. I'm Jose Pablo, and I'm continuing with the case studies. So the idea here is to present you what are the application of this reference network model. So, for instance, we have used it to compute the cost of increasing share of distributed resources such as PV, wind power, combined heat and power storage, demand response, electric vehicles, on distribution network investments and cost at the end. And then how the allocation and operation of DERs may affect the planning and the operation of distribution networks. So these are questions that we can answer with this model. So how do we, what's the process to get these answers is we start with some substations and consumer locations. So we start here. We build the initial network, And then as well, we select a scenario for the distributed energy resources connected at different voltage level locations, and we have the hourly profile of these resources. So based on these two, we have an initial network using the greenfield model. So we have our initial reference network, and then we can assess the cost of the distribution cost in terms of low voltage feeders, medium and low voltage transformers, and medium voltage feeders. So I'm going to present 4 case studies briefly, very briefly, because we have short time. We start with solar PV penetration, then we continue with demand efficiency and demand response, electric vehicles, and the case of rural, the application of this model as a support tool for rural electrification. So here you see the impact of solar PV on distribution network cost. This is an exercise that has been applied for the MIT solar study. So the idea was to compute what are the needs for reinforcements if we increase the share of solar PV. So this is a network in the US, and so as we are going to see is we are going to increase the penetration of solar PV, and we can see what is the effect on the network reinforcements, transformers, and substations. So by increasing the share, we can see here we add in yellow more PV, and then we can see what happened with the transformers, the red dots, and also with reinforcements that are represented in green. So as we increase the share of solar PV, we see that more reinforcements are needed, and this is the results. So we have here the reinforcement needed in this area. This is a urban area, and so in terms of network reinforcements, and also we can compute the associated cost for different penetrations of solar PV. This example was done without considering the inverter capability to control voltage limits, but that is also could be implemented in the model. So the next case is the case of active demand response. So this is work done for a European project, advanced project, and we follow the following methodology. First, we have the consumers. We have information about the geography, the peak demand, as well the electrical limits and the equipment, the standard equipment for the network. Then, based on this, we can build a representative network using the greenfield model. Then, for new, we have a scenario for new peak load and for active demand programs. So we incorporate that, and we can see on that initial for the future what could be the needs for reinforcements in order to have a certain quality of supply and limits on energy targets on energy losses. So what the different active demand programs can do in terms of potential savings for the distribution networks. So for instance, here we represent, there were 2 different measures. The first one was on energy efficiency, and the red lines is the without active demand, as you see in both sides. In here you have different energy efficiency programs that what they are going to do is to reduce the load profile, and here for the 24 hours. And then you have different programs such as information bill, website information, in-house display, and we can see what is this was a pilot project, and so it was possible to measure what were the effects of these different programs, as well as demand response, so shifting some demand from peak hours to off-peak hours, for instance. And so we can see that the low duration curves change during these 24 hours. So in terms of the cost and the reinforcement needs, as you see here, without active demand, you see here long reinforcements, more in red, and with the maximum potential that was computed in the project, so you need less reinforcements for future demand growth. This is for the urban network, and same in terms of, for instance, transformers. You have here more red dots for the transformer reinforcement in comparison with this case with active demand. So in terms of final results from this, some of the results from this project, you can see here for rural and urban networks using dynamic pricing and using the baseline, the optimistic case. So for the potential of for the optimistic case, we can see that from this no demand response, or the baseline case, we can have significant cost reductions for all the cases. And for the technical potential is dramatic. The further reductions that you can that are expected, but it's not realistic. So it's not that realistic that all the consumers. This implies that all the consumers and all these networks will engage in this program. So what it was the end concluded is the optimistic one was the case that is more realistic. So now there was another case to measure the impact of electric vehicles. So for that, there were different networks model. So the tourist, for instance, the tourist network, rural, big cities in Spain, and also a city in Greece. And as you see, there was a very big distribution area in the order of thousands of hundreds of thousands, consumers, and as well as you see here the number of substations, so the area, number of substations, and number of consumers. So this area were significant high, big. So for that, we have the different profiles, so different charging strategies for electric vehicles. And the first one is what is called the dumb charging. So basically, we have here the residential load, the industrial load, and on top, when the consumers arrive home, they start charging the electric vehicles. This will imply an increase on the network, on the peak demand. Another possibility is to have some time of use tariffs. So the electric vehicle responds and will charge at the hour of the lowest price, or as more smart charging that take into account not only the energy price but also the network loading. So for all these cases, the results were that so for the different case studies, the reductions in terms of the increase, in terms of network investments were significant for all the areas in case of the dumb charging. Especially, for instance, here the rural areas, the medium here for the rural area, the medium voltage feeder. And here is shown the effect on the different strategies. So for the smart charging, for all the areas, the cost, the percentage of reinforcements here represented were the lowest, and then is significant in case of the peak charging, because this will increase the load in the feeders, and then more reinforcement are needed. And this is the case for the different for all the areas. So finally, there were also some sensitivities in the case of what is the reinforcement cost with the increasing level of penetration, and then the cost for the medium voltage, low voltage transformers, the low voltage feeders, and the medium voltage feeder. And for increasing penetration, and where the scenario 3 is the one of highest penetration in 2000 for the horizon 2030. Finally, this, as I told before, this reference network model is a tool that has been used to complement another tool that has been developed in our institute, that is the reference electrification model. The idea of this model is to look at the best strategy for rural electrification, taking into account network reinforcement, microgrids, or isolated systems. So the objective is to minimize the total cost, and the RNM, the reference network model, is used to compute the cost of reinforcements of the network, and it's a benchmark for other alternatives, such as microgrids or isolated systems. This model has been used, for instance, in a big area in India, in the state of Bihar. And so the state of Bihar is North India, and then there is this district in the state, and with more than 3.5 million people and 600,000 inhabitants, more or less. And the area is around 2,000 square kilometers. So, for instance, there are different solutions for instance, in this area, in here, you can see the 11 kV and so the low voltage reinforcement needed in order to interconnect and to provide electricity to all the consumers in this area. But in this other area, the best solutions are mainly microgrids, and also there are here some isolated systems, so not connected to the rest of consumers. And so the reference electrification model provides a graphical representation as well. So as you can see, using Google Earth files, and as well it computes the best configuration to electrify. So finally, as a conclusion, the reference network models depends a lot on the sizing criteria. For instance, to what is the reliability margin that has to be maintained in every hour in a certain region, or the continuity of supply targets, as well as the standard catalog that is used as inputs for the model, as well as technical economic parameters, as Carlos was explaining in the beginning of this webinar. These criteria are necessary to run the model and obtain a reference network, and the results depend a lot on the criterion used to expand the networks. The reference network models are different from real networks, but they are a benchmark and depend on the criteria that has been used to expand the networks, and but the results are very similar, as has been compared with a lot of projects that we have been running here. Then the reference network model is a tool to support the regulator, for instance, and to reduce the asymmetry of information between distribution companies and the regulator in order to remunerate for investments on distribution networks. Then it has been used to estimate the network cost, the distributed generation impact, or in general, distributed energy resources, energy losses, and quality of services of different areas. So the cost of meeting those requirements is an objective estimate of costs that are efficient, and this model has been used to build also synthetic networks that can be used for different analysis. So here are some of the projects that has been where reference network model has been used. For instance, it has been used for building the Chilean networks for a case study for these consultant companies, CINEX and SysTep. Then there has been used for a Spanish manufacturer to build urban, semi-urban, and rural networks to meet cost-benefit analysis for storage, for instance. So what is the value of storage at different networks, different configuration of networks. It has been extensively used, currently used by the Spanish regulator to plan distribution system in Spain for taking into account real customers' coordinate for an area of 500,000, more than 500,000 square kilometers and 27 million customers. This is not at once, but in simultaneous computing. Then it has been used by the MERGE project, building 5 distribution networks in Spain with real consumer coordinates, and also in Greece, as I explained before, for advanced project in order to compute in different locations to compute the effect of active demand programs, the in progress project to compute the impact of distributed generation, for the utility of the future study and the future of solar to compute the effect of distributed resources and the utility of the future, as well as compute distribution network tariffs based on different networks, for the DSO observatory to have representative networks for Europe, both including medium voltage and low voltage feeders. And finally, as Carlos explained, it has been applied as well in the US for building representative network for US synthetic networks, and this has been financed by the Department of Energy. So finishing with that, Carlos now is going to quickly,
very briefly, because we only have 2 minutes. So some homework is to build a full distribution network using a trial version of reference network model which is available on the web. Here is the URL to use this trial version. So here you have some explanation on how to use this trial version, explaining how to make it in detail. You can see it later. And these are results of the model. So just very briefly, I will show in more detail this model. So here, this is the trial version of the model. It is available in this URL. Here you can access the trial version. So you first have to select the input image with a street map. Then you have to set the scale. In this case, this distance corresponds to 100 meters. You have to see this in the original image, and this scale must be close to 1 pixel per meter. Then you select the block of buildings. So you have to select the buildings, but also this color for the block of buildings. Then you set the parameters of the consumers here, and you can check the catalog of the model here with all the parameters, and then you start building the network. Then the model starts, and the results will last about 1 minute. Here I have them saved. These are the results of the model. Here we have selected the color of only the buildings, not the block of buildings. So you obtain the result where you don't correctly identify the block of buildings. If you correctly identify the colors of all the blocks of buildings, then you get the result, which looks more like a real estate map, and this network, which is more realistic. And you also get some files here. So you get some files to be able to run a power flow in MatPower. This is the file for MatPower. You can run a power flow with this network. You also have the figures that you obtain with the model, and also a summary of the network with the customers, the electrical lines, the length of the lines, the substation, and some summary in terms of investment cost. Well, That's all from the presentation. I think we can start now with the questions.